One very important continuous distribution is the exponential distribution. Where it comes from, though, is it actually stems from a Poisson process. Remember, with the Poisson distribution, we were looking at we knew the mean number of occurrences or successes in a time interval was lambda. So it stands to reason that if we look at the time between two occurrences, that would be the reciprocal of that, which is 1 over lambda. So right away we know that our exponential distribution has a mean of 1 over lambda. As it turns out, the equation of the density curve for the exponential function, because a time between two occurrences can be any kind of number, it could be decimal, it could be whole number, but it's continuous in nature because it has to be measured as opposed to being counted, is we have lambda e to the negative lambda x, f of x equals lambda e to the negative lambda x. Here, x can only be non-negative, greater than or equal to 0. So we have a sample curve of what that might look like here. So we have this density function here. Now, we need calculus to show this, but the area under the curve is 1. Okay, so one thing we need to be able to find are cumulative probabilities. It turns out, as opposed to the normal distribution, which we needed to use tables to find cumulative distributions, we actually have a formula that we can use for the exponential distribution. If we want the probability that x is less than or equal to a, I'm just going to pick a value of a here. The probability that we're less than or equal to a, and that automatically means that x is between 0 and a, because we can't really have a negative time, is 1 minus e to the negative lambda a. And that means that the probability that x is greater than or equal to a, just subtracting that result from 1, this area is e to the negative lambda a. Okay? Now, one thing to note, and I'm just going to draw another exponential curve here for us, is that you notice that this curve is what I would call severely skewed to the right. It doesn't even have a gradual uptick before the peak, before it comes down again. It just starts high and goes down. So remember that means, since it is skewed to the right, that we know that the mean is greater than the median. Now remember that the median is the value that lets half of the distribution to the left and half the distribution to the right. So that would probably be about here on our curve. So I'm going to say that that is the median, and the mean is going to be a little bit higher because, again, those high values are pulling the average up. So it stands to reason that the mean will be greater than the median. Now, if we come back up here and look at these formulas, and everything we need to know about the exponential distribution is pretty much right here. We know that the mean is already 1 over lambda. We have the median is the natural log of 2 over lambda. Now remember that the natural log of 2 is about 0.7. It's actually 0.693 with a bunch of other numbers. That means that multiplying the mean by a number smaller than 1 is going to make it smaller, further emphasizing that, yes, the median is less than the mean. Notice also that the standard deviation is the same as the mean. It's a very unusual result, and again, it comes from calculus, but that is very true about the exponential distribution. So let's take a look at a specific example. So let's say that we have an event where we expect the event to happen 15 minutes apart. So that means that I'm going to have a mean rate of 15 minutes. And notice that the mean rate, lambda, and the expected time, 1 over lambda, are reciprocals. So this means that lambda is equal to 1 over 15. Okay, so let's say we want the probability. Let's say that we want to know the probability that it takes between 10 and 20 minutes. Actually, let's change that just one moment. Let's just go to, let's say, what the probability that it takes less than 10 minutes. Which is technically the probability that x is between 0 and 10. So thinking of an exponential distribution, we do have something like this. Here's 0. Our mean is 15, so that's up here. 10 is here. So we're probably looking at a probability that's close to 1/2. Now, according to our formula, This is 1 minus e to the negative lambda a. And we already know that lambda is 1 over 15. And here, a is 10. And we could simplify this if we really wanted to. This is really 1 minus e to the negative 2/3. And let's just pull out our calculator here and see what that is. So 1 minus e to the negative 2 over 3. And we get just about 0.5. It's 0.4866. Okay, so the chance of something taking within 10 minutes is almost half. So now let's think about another problem here. What is the probability that, let's say we want to know what the chance that something takes more than 20 minutes. Maybe there's some kind of guarantee or something, some kind of incentive will offer if a phone call takes more than 20 minutes to come or whatever this thing is. So using the formula, we know that this is e to the negative lambda a from above. So here a is 20 and lambda is still 1 over 15. And this is e to the negative 4/3. So again, using our calculator, let's see what that is. So e to the negative 4/3 is 0.2636. So still quite a considerable probability. Now, what if we want a probability of a range? Let's say we want to find the probability that it takes between 30 and 40 minutes. Well, if you think about the curve and how it works, let's say here's 30 and here's 40. So we want this area here. Well, what we can do is we can find the probability that we go up to 40 because that's something that we know. And we can find the probability that we go up to 30 because that's a probability we don't want, right? And then we know we can subtract them. So the probability that x is less than or equal to 40, well, that's 1 minus e to the negative 40 over 15 and 1 minus e to the negative 30 over 15. And we can put that into the calculator just as it reads. So we have 1 minus e to the negative 40 over 15 minus, parentheses, 1 minus e to the negative 30 over 15, which, yes, we know that's 2. And that's what we get for our answer. So that event is going to happen about 6.59% of the time. So we subtract those. And that is how we find probabilities with the exponential distribution. I thank you for watching, and I hope that this helped you.